Section 9.3, this time we're going to do significance tests with a population mean. 9.2 we did parameter, this time we're going to look at the mean, okay? So similar to what we did in chapter 8 when we were doing confidence intervals, when we try to use the z statistic for the mean, the problem is we need to know the population standard deviation, which we almost never do. And so if we're going to use sample standard deviation, then that means we need to switch to t distribution. Okay, so just like with confidence intervals, when we're doing significance tests for the mean, we're going to use the t distribution, which means our standardized test statistic, it's a tough one to say, is going to be the t instead of z. Okay, we didn't talk about using table B because it has some limitations as far as what degrees of freedom it shows. So your best bet is to use a calculator to find the p-value. So here are the steps for that. Okay, very similar to what we did for proportions in the last section. We're going to the tests and we're choosing t-tests. Okay, so t-tests on the TI. In the Casio, we're choosing the t-menu and then one sample, one S. Okay, and then just like before, we're entering the pertinent values and then choosing the direction that matches our alternative hypothesis. So let's look at an example. All right, you can pause and read through this, but the process is going to be the same as in the last section. We're going to do our state, plan, do, conclude. Okay, so in the state part, we need to state our hypotheses. We need to identify the significance level and define any parameters. Okay, so in this case, our null hypothesis is that the mean is equal to 5. Our alternative is that it's less than 5. And then we have to make sure we define that the mean that we're talking about here is the dissolved oxygen level in the stream, and our significance level is 0.05. Then for the plan part, we need to identify the method that we're going to use and check our conditions. Okay, so we're doing a one sample t-test for the mean. The conditions are going to be the same as they were for confidence interval for the mean. So random, less than 10%, and then either a normal or a large sample. So again, this is just like with confidence intervals. It's got to be one of these three things. Either the population is normally distributed, which is information that would be given to you in the problem. The sample size is at least 30. If both of these things are not true, then we're drawing a graph and looking for any strong skewness or outliers. Again, I would suggest using your calculator to draw the box plot because it will identify outliers for you. All right, so we picked random locations. We were talking about locations along the stream. Like there's no limit to how many locations. If I move my hand over 3 inches, that's technically a different location. So 10% we're good. And then we draw the graph. There's no outliers. It's almost perfectly symmetric, so we can meet that condition. All right, then for the do, this is the part where we're going to use the calculator, and we're going to write 3 things for this part. We're going to write the sample statistics, so the X bar, the sample mean, and the sample standard deviation. We are going to give the standardized test statistic, which would be the t value, and then we're going to find the p value. Okay, so all of this can be found on the screen where you enter or when you do the test on your calculator. And we also want to report degrees of freedom. That's again going to be n-1, just like it was for confidence intervals. So sample statistics, all right, standardized test statistic, the t value, degrees of freedom, and then the p-value. And last step is conclude, and we're using that same conclusion sentence as before. So because the p-value in this case is greater than our significance level, we're going to fail to reject, and we do not have convincing evidence that the true mean oxygen level is less than 5 milligrams per liter. All right, this second question, what kind of mistake could we have made? And what would that mean in context? We failed to reject. Okay, so the option that we have here is potentially making a type 2 error, which would be if I fail to reject when I shouldn't, when the alternate hypothesis is actually true. So if I fail to reject, that means that I think that the oxygen level in the stream is okay. It's at least 5, but it's really less than, and I wouldn't be able to detect this, so that could be dangerous for anything that lives in that stream. Okay. Something that you need to know is when we are doing a two-sided test, okay, so that's like the equal or not equal, confidence intervals give us the same result. So what that means is if I do a 95% confidence interval and the null hypothesis value is in that interval, then I would fail to reject, okay, because that means I don't have evidence for the alternative. If I make a 95% confidence interval and the null hypothesis value is not in that interval, then I would reject that null hypothesis. Okay, this only works for a two-sided test. Okay, and it's like the inverse of the significance level. So if alpha is 0.5, then I would do a 95% confidence interval. If alpha is 0.01, it would be a 99% confidence interval that would give me the same results. Okay, so you can read through this example, pause and read. All right, so our hypotheses here are that the mean is 31 or it is not 31, because we would just want to know if the weight is different. Okay, so this, because it's equal or not equal to, this means this is a two-sided test, which means we can use a confidence interval in addition to or in place of a significance test. Okay, so we check our three conditions, just like before. And then the confidence interval goes from 31.255 to 32.616. So 31 exactly, like 31.0, is not part of this interval. That means I need to reject the null hypothesis. All right. So I have convincing evidence that the true mean weight is not 31 ounces because 31 is not part of this interval. Okay. And then the last question, just kind of a throwback to the very beginning of the year. Can we conclude that the irrigation system caused a change in the mean weight? And no, because we didn't do a randomized experiment. All right, so we can say that there's a relationship there, but we can't say that one caused the other. All right, so when we talk about significance tests, we have something that's called the power. All right. It's not something that you're going to be asked to calculate because it's kind of a complicated concept. But what you should know about it is it's a conditional probability. So what is the probability that the test rejects the null hypothesis given that it is false? Okay, so basically like the probability that the test finds the right answer. Okay, if my null hypothesis is not true, the probability that my test rejects that not true hypothesis, that is referred to as the power of the test. All right, and power and the probability of making a type 2 error have to add up to 1. Okay, so if I'm given the power, then that is 1 minus the probability of type 2 error. And then the inverse is true. If I'm given the probability of making a type 2 error, that is 1 minus the power. All right, so you can pause and read through this example. Okay, and here is our interpretation sentence for power. So if, and they give you a number. So if the true mean lifetime of the company's batteries is 31 hours, okay, if it actually is 31 hours, then there's a 0.762 probability that the test will correctly reject the null hypothesis that it is 30. Okay. When we talk about the power of a test, okay, more power would be better, right? So a higher number there would be better because we want to reject the null hypothesis if it's not true. So what are some things that we can do to increase the power of the test and decrease the probability of making a type 2 error? Okay, we can increase the sample size, all right? Increasing sample size decreases variability, which makes it more likely that we get the correct result. We can increase the significance level. Okay, so if I go from 0.05 to 0.10, that also increases the power of the test. Well, also any increase in the distance between the null hypothesis and the true parameter value. So, for example, in this one, the mean was 31, and 31 is 1 away from our null hypothesis of 30. So if the true mean was like 34, that test would have a higher power because the real value, even though we don't necessarily know the real value, but the real value would be further away from the mean. So there's a better chance that we would reject that hypothesis. Now, each of these things comes with a drawback. Okay, increasing sample size is sometimes expensive or impractical. If I have to find more people, find more things, it can be difficult to do. If I increase the significance level, yes, I increase the power and I decrease the probability of making a type 2 error, but at the same time, I am also increasing the probability of making a type 1 error. Okay, so everything is a trade-off, and we have to balance, again, which one of those errors is going to be more serious. Increasing the distance between the null hypothesis and the true value, we don't have any control over that. It's just sort of a fact that you should know that the further away we are from the null hypothesis, the higher the power, but it's not something that you can really do anything about. Okay, and that's it for 9.3, guys.